Okay, so today we're going to look at quantity to quantity stoichiometry. So this is going to be where we start with a quantity, so it could be in mass or it could be in liters, and we want to end in a quantity of some other part of the chemical reaction, once again, in either mass or liters. Let's get going. So quantity stoich, it's very similar to the recent stuff. We'll get some more practice time. I'm just going to run through 5 different examples with you today, and let's get going. So in the instance in which you are provided with a quantity of a substance and are asked to calculate a quantity such as the mass, volume, or concentration of another substance, quantity to quantity stoich is used. This is basically the same thing as the previous methods of stoichiometry we've done before. Not a huge surprise. Remember, the only thing that carries over from one compound in a chemical reaction to another compound is, of course, the number of moles. So let's start with this very first example. What mass of aluminum oxide must be decomposed to produce 80 grams of oxygen gas? Well, first of all, got to start with your balance equation. So with aluminum oxide, if you check the charge on aluminum, it's +3. Oxygen has a 2 negative charge. Swap and drop, that's going to be Al2O3. This is a decomposition reaction, so that means it's going to be breaking down into its constituent parts. So it's going to form aluminum plus oxygen gas. And remember, oxygen is part of Hofbrinkel. It doesn't exist on its own, so it has to be O2. Next up, of course, we got to balance this. We look like we need to have 2 aluminum right here because there's 2 aluminum on the left-hand side. But unfortunately, there's nothing we can multiply O2 by to turn it into O3. So we're going to have to kind of play around with this a bit. I'm going to start by maybe putting a 2 in front of this to turn this into 6 oxygens. And then that means I can put a 3 in front of this, so we can have 6 oxygens on this side. And now notice on the left side, we have 4 aluminums, so we have to put a 4 in front of it this time. So now it's balanced. It was just a little bit of extra work on that one. Step 2, determine the givens and the unknowns. You've noticed in the past few lessons, I've done this like this little section, the first example, always a little different. I say, oh, we have this, and then we want this. You know what? In this one, I think I just might make it like a little bit more standard, like what I've been doing for everything else. Literally just draw a line underneath the thing that you have. We have 80.0 grams of oxygen gas, right? What we want to have is the mass of the aluminum oxide. So we want the mass of this. Well, one thing I need to highlight here is, remember, the only thing that can carry over from one piece of a chemical equation to another piece is the number of moles you have. And the question didn't give us how many moles we had of anything, so we actually have to calculate that first and then use the moles and the molar ratios, that's the coefficients in front of each of these, to figure out the amount of moles of the thing we want before we can figure out the mass. Well, first things first, let's have a look at our 80 grams of oxygen. Notice it's oxygen gas. That means we're going to have to take 2 times the molar mass of oxygen, and the molar mass of oxygen, I believe, is 16.00. Which means the molar mass of oxygen gas, that's O2, is actually going to be 32.00 grams per mole. Now you can, of course, just set this equal to some amount of grams, which we actually have, 80 grams, divided by some amount of moles. I'll just call it N, because N is usually the symbol we use for moles. And then, of course, to get N by itself, you just multiply it over and divide by the 32. So this is going to give us N equals exactly 2.50 moles. Now, here's the thing. I want you to notice that 2.50 moles represents the amount of moles of oxygen. And the amount of moles of oxygen, according to our coefficient here, is 3 parts. What we're looking for is the amount of aluminum oxide. Now, aluminum oxide only has 2 parts. So perhaps what we should do is we should divide 2.50 by 3. So divide it by 3, that would tell you what 1 part is. And then I'll just do this all in one step. I'll times by 2 right afterwards to find 2 parts. So long story short, if we take 2.50, divide it by 3, and then times by 2, we should get the number of moles of aluminum oxide to equal 1.666 repeating, okay? And that is in moles. Now remember, the question itself is asking us to find the mass, so we should use the molar mass of aluminum oxide to figure out that now. I might as well go down below step 3, might as well use that space now. The molar mass of aluminum oxide, notice we have 2 aluminums. Don't use the coefficient in calculating the molar mass. Forgot to mention that earlier. You always just look at the actual element itself. The coefficient is only for dealing with the number of moles, not the molar mass itself. So we have 2 aluminums. So that's 2 times, what's the molar mass of aluminum? 26.98. plus 3 times the molar mass of oxygen, which is 16.00. This gives us the molar mass of aluminum oxide to be 101.96 grams per mole. And let's wrap this up. We'll just say, all right, this is going to equal some amount of grams. We'll say that's X over some amount of moles. That's going to be 1.6 repeating. Just throw like literally like a boatload of 6s on there and then finish it off with a 7. Because we only want, I guess, 3 sig digs in our answer, but we might as well use as many digits as we can. Multiply that 1.6 repeating over to the other side, and you're going to find that X is going to equal, rounded to 3 sig digs, 170 grams. So in other words, in order to get 80 grams of oxygen gas out of this, you would have had to start with 170 grams of aluminum oxide. It's very important to note that these coefficients out in front in the balanced chemical equation will not work on grams. You have to use moles, and the reason being for that is it's the amount of molecules themselves actually occurring within this reaction that really matter. Mass does not relate directly to the molecule itself. It relates to the molar mass. So it's important to make that distinction. All right, number 2. An excess of zinc metal is reacted with 250 milliliters of that much concentration of hydrochloric acid. What volume of hydrogen gas at 25 degrees Celsius and 95.0 kilopascals can be produced? Holy smokes. Okay, we got a lot of like little bits of information here. I'm going to start just by getting a chemical formula down. We're reacting zinc with hydrochloric acid. So zinc, Zn, plus hydrochloric acid, that's HCl. It's asking us what volume of hydrogen gas is being produced. So spoiler alert, that's something that's going to be made here. But this is just going to be a single replacement reaction. So I might as well pull that hydrogen gas out first. So H2 plus zinc chloride. And just remember, zinc has a positive 2 charge. Chlorine has a negative 1 charge. So you're going to need 1 zinc and 2 chlorines. To balance this, I think we just have to put a 2 in front of the HCl, because now we have 2 hydrogens on both sides and 2 chlorines on both sides. Looks like we're pretty much good. So this is where we are going to start having to figure out how many moles of stuff we have here. Well, if we look at the question, notice we know how many milliliters of hydrochloric acid we have, and we also know the molar concentration in moles per liter. Since this is in moles per liter, if we just multiply this by liters, we can knock the liters out and we'll be left with moles. So let's focus in on that hydrochloric acid. 0.100 moles per liter equals some amount of moles over some amount of liters, which is 0.250 liters. Like I said before, just multiply this over, and you're going to get the number of moles you have of that. So the number of moles in this case is going to be 0.025 moles. Now, you should also recognize here, because this is our number of moles, this is going to represent 2 parts, right? I always write this in. You don't have to write the 2 parts thing in. I just do it just to help guide you. But there's 2 parts of that here. We're looking for the volume of hydrogen gas that's going to be produced. So notice the hydrogen gas in this chemical equation is only 1 part. So we should divide this by 2 to figure out how much moles of hydrogen gas we're going to have. Since we're dividing that by 2, 0.025 divided by 2 is going to give us 0.0125 moles. And that's our number of moles of hydrogen gas. But we're looking for the volume in this case. Remember, volume is measured in liters. So we have to try to figure out how to connect that. Well, there's a temperature that they gave us, and there's a pressure. This is kind of leading into the classic ideal gas law. And the ideal gas law, which I did reintroduce to you guys yesterday, is PV equals nRT. Notice we have a pressure. We want a volume. We have N. We have R, because R is always 8.31. And we have a temperature, but the temperature is in Celsius, so you just have to add 273.15 to it, and you're going to find that's 298.15 Kelvin. Long story short, just throw that into PV equals nRT. So we've got 95 times V equals N, which is 0.0125 moles, times 8.31, which is always what R is equal to, times by 298.15. Really, you just have to multiply all this stuff together and then divide by 95. You're going to find that V is going to equal, at least as far as I got 0.2 sig digs here, 0.33 liters. Hopefully that's pretty good. We're going to move on to the next example. Riveting stuff. I know, it's super, super exciting. This is like the 4th day in a row of the same kind of material, but it is important to gain practice of this. So I'm just helping you understand. All right, this next one here, you know what, I'm not going to ramble too much on this one. I bet you guys probably just want to clear through this, but you do need some practice. I'm going to ask you, pause the video here, give this one a try. It's very, very similar to the last one we just did. So pause the video here, give this one a shot on your own, and then I'll go over it in a second. All right, I'm going to go over this one. I'm not going to waste too much time on this one. We're neutralizing H2so4 with NaOH. I think we had this exact same formula last class, but whatever, we'll build it anyway. So H2so4 plus NaOH becomes, it's going to be a double replacement neutralization reaction, really. So it's going to be an HOH that gets formed, that's water, plus sodium sulfate. Sodium is going to be Na2SO4. And then to balance this, we just have to put a 2 in front of this and a 2 in front of this, and we're good to go. If we're looking at what we've actually got here, we were given some information about H2SO4. So if we bring that down, we know the molarity, 0.100 moles per liter. This is going to equal some number of moles over the number of liters we have, which is 0.020 liters, because that's 20 milliliters right there. Multiply that over, you're going to find that N is going to equal 0.002 moles. And notice that that's only one part. The thing we're looking for is NaOH. NaOH is 2 parts. So we just have to multiply this by 2. So the number of moles of NaOH is actually 0.004 moles. Now, it is asking for a volume of this that would be required. The only other thing we know is that we have a molar concentration of 0.150 moles per liter of NaOH. So once again, maybe we could use that to be useful. So 0.150 moles per liter equals some amount of moles, which we know, 0.004 moles, over our volume, our number of liters. I'll just call it V for volume. Multiply by V, divide by this, you're going to find that your volume is going to equal, rounded to, I guess, 3 sig digs here, 0.0267 liters. So that would be 3 sig digs, so that would be a good answer, but that's kind of uncomfortable. If you just times this by 1,000, you'll see that that's 26.7 milliliters. So regardless, however you wanted to put your answer, that would be what you could do there. All right, here's another one, just a little bit of a heads up here. We've got nitrogen combining with, oh, it doesn't even say. It says what volume of nitrogen at a pressure of this would be required to create this much ammonia. Well, it's going to be nitrogen combining with hydrogen, because ammonia, hopefully you know, is NH3. So in order to create ammonia, you just have to combine nitrogen with hydrogen. And it mentions this Haber process. I think that's how you pronounce it. I'm not 100% certain. Honestly, like, that's irrelevant. You don't need to worry about that. There's like a whole big description on page 17. I'll even write that, page 17. If you're interested, you can read about it. It really isn't that important. So you can even just cross that out. Not super important. But the question itself is still decent. We're looking for the volume of nitrogen. We were given a pressure and a temperature. This is kind of already illustrating we're going to be using PV equals nRT. I'm going to start you off with the formula here, and then I'll let you guys try this one on your own. If we're combining nitrogen with hydrogen to make ammonia, this is going to be N2, because nitrogen is part of Hofbrinkel, right? So it's N2 plus H2 becomes NH3. And in order to balance this, we probably have to put a 2 in front of here. So we have 6 hydrogens in total. We have 2 nitrogens for sure, so that's all fine. With 6 hydrogens on the right-hand side, we have to put a 3 in front of it here. And bingo, bango, bongo, we're all done right there, right? No big deal, okay? So what I want you to do on this one now, I want you to pause the video here, give this one a shot, see if you're able to solve for it. All right, going over this one now. It gave us the mass of ammonia that gets produced. Now, mass can be turned into moles by using your molar mass. So I think we might want to start by finding our molar mass of NH3. Molar mass of NH3 is going to be 14.01, that's molar mass of nitrogen, plus 3 times 1.01, that's molar mass of hydrogen. This is going to give you 17.04 grams per mole. We know how many grams we have. It's that ridiculous 36.9267 grams. We don't know how many moles we have. Times by N, divide by 17. We're going to find N is going to equal, bear with me on this, I'm going to keep a ton of sig digs here, 2.1670599 moles. Now I want you to recognize this is 2 parts according to our balanced chemical equation. We're looking for the volume of nitrogen. So that tells me we should probably find the number of moles of nitrogen, which notice is only 1 part. So we should take this number and divide it by 2 yoink, divide it by 2 to find that the number of moles of N2 is 1.0835299.5. 2995. Perfect. Moles. Okay, now where? All right, so what we're looking for is volume. Now volume, like I mentioned earlier, just given the stuff that they're telling us here, probably going to use PV equals nRT. So we're looking for V. We have pressure. We have the number of moles. R is always given. And we also have a temperature. It's this 39.7939 degrees Celsius. Let's quickly turn that into Kelvin. Remember, you just add 273.15. That's going to give us a temperature of 312.9439, and that's Kelvin. Long story short, throw this into your ideal gas law, right? So in other words, we know our pressure, 136.46. We're looking for volume. This is going to equal our number of moles, 1.0835299.5. It's like the world's worst phone number. Then we got R, which is 8.31. And we got our temperature, which is 312.9439. Why'd they have to use so many digits on this one? Jeez Louise. It's just wasting our time. Anyway, V is going to equal all of this stuff on the right-hand side, multiply it all together. Once you have an answer for that, divide it by 136.46. Then round to a whopping 5 sig digs on this one. You're going to find it's going to be 20.649 liters. And that's pretty much about it. That's all we really got to do on this one. All right, moving on. Last question. This, I kind of chuckled when I was making my answer key for this because it's like, this is like the same thing we just did, right? This is like the exact same question all over again, except it just gave us like a different amount for a different thing, but whatever. Anyway, so long story short, I'm not going to get you guys to try this one on your own. I'm going to blitz through this as fast as possible. Some of you guys are going to have to like make good use of the pause button here, but you know what? We're going to do this live. We're going to run for this. It's going to be like chemistry Olympics here. Okay, buckle up here. Buckle up, boys and girls. Here we go. So here it is. Once again, same reaction. Oh, see, I got too quick there. See, I got too quick. Got to calm down. Anyway, same reaction. So it's going to be N2 plus H2 is going to become NH3. We need 2 of these guys. We need 3 of these guys. What do you know? It's balanced. Next thing we got in here, we know how many kilograms of hydrogen we have. Ooh, exciting, right? So hold on. Yeah, we do know. Okay, we're good. Sorry, I was just a little worried. Okay, we do know how many kilograms of hydrogen we have. That's 7.5 kilograms. Kilograms, those are no bueno. We don't want to use those. We want to change that into grams, 7,500 grams. Okay, so next thing. We want to use our molar mass of hydrogen because grams, nobody cares about grams. We want them in moles, right? So in other words, molar mass of H2 gas is just 2 tons of molar mass of a single hydrogen. So 2 times 1.01, that's 2.02 grams per mole. Okay, so 2.02 grams per mole. This is going to equal 7,500 grams over who knows how many moles. Multiply by N, divide by 2.02. We got the single most number of moles I think we've ever seen in our entire life. Holy guacamole, am I right? 3,712.871287 moles. I kept pretty much all the digits that came up in my calculator because why not? I want this to be accurate. Now, take a wild guess. Shout it at your screen here. How many parts is this number of moles? 3. Yes, it's 3 parts. So this is 3 parts for our H2. We are looking, however, for a volume of ammonia. So we need to worry about the ammonia right here. So we want 2 parts. So why don't we just take this number and divide it by 3 to get 1 part. And then in the same step, because why write it down, times it by 2 to find 2 parts. So our number of moles of ammonia that we get is going to be 2,475.247525 moles. At least that's what I got, at least, right? If you're off by a little bit down here, who really cares, right? It's all going to work out. That's why I keep a whole bunch of digits. It makes it pretty accurate in the long run. All right, last up here. We're looking for a volume. We have a pressure. We have a temperature. You know, I think we could probably read it by now. We're going to have to use the ideal gas law once again. PV equals nRT. We have pressure. We're looking for volume. This is our unknown. We have this, and we have this. The one thing I want to say, though, about that 80 Celsius, remember we should add 273.15 to turn it to Kelvin. 80 Celsius is the same thing as 353.15 Kelvin. So that's what you got to throw in that equation. Long story short, here we go. Let's see if I can fit it in like this little bit of room I got here. Pressure is 450. Volume is what we're looking for, so I'll leave it as V. N, maybe I should take it back. I don't think N's going to fit in here, but you know what? We'll try. We'll see what we do. 2,475.2475525. Good enough for me. R is always 8.31. Temperature, yeah, I'm going to have to give up here. Temperature is 353.15. Yep, there we go. Multiply that whole right-hand side together and then divide by 450. Long story short, to only 2 sig digs. That's really annoying. You got like 16,000 something liters as your answer. Like this is going to be a really big number, but to 2 sig digs, you have to write this as 1.6 times 10 to the 4 liters. So I guess the only thing special about that one is like the first time in a while we've actually had to use scientific notation because we only had 2 sig digs. Okay, I've like totally beat this to death, but some of you guys are looking at this right now. For those of you who are watching this on the right time, you're like, oh, it's Friday. Is he seriously teaching us the same thing we've been doing all week once again? My answer is yes, I have. And I'm recording this at 10:22 p.m. December 1st, and I'm getting a little bit sleepy, and that's why I'm getting kind of crazy here. But anyway, last slide in here is just talking about page 17. It's that Haber process. You don't need to know anything about this. I don't know why this is in here. Basically, it's just a process by which they make ammonia. There's like a little history lesson in there about like the early 20th century. Read it if you're interested. You don't need to know it. So for practice today, I want you guys working on page 18 to 20. I know there was a whole ton of questions on like, what was it, page 11 to 14 from the last day. This one doesn't have nearly as much, but there's still quite a good amount. So my advice for today, really, I'm just going to make a rule right here. At very least, do the even number questions, right? At very least. I'd appreciate it if you did them all, but I totally understand looking at like 13 or whatever questions in here. There's quite a lot. So if you do at least the even number ones, you should have enough practice, but otherwise do more if you feel the need. The back of the book has all the answers. I know I'm sounding like a broken record by saying that. And another broken record thing I'm going to say right now is if you have any questions, you guys know I'm available in Zoom. Just pop right back in at any point and I'm able to help you. Anyway, best of luck. Enjoy.